All right, let's dive into one of the most powerful and honestly elegant tools in the entire machine learning toolkit, the Support Vector Machine, or SVM for short. This thing is a total workhorse. It's used for classification, regression, you name it. And it has some seriously clever tricks up its sleeve.
I just love this analogy because it really nails what makes an SVM so special. You know, it might not be the giant sword you use for every single task, but for those tricky, complex problems, especially with smaller datasets, it's like a surgeon's scalpel. It offers a kind of precision and power that's just tough to beat.
Okay, so let's get right to it. What is the fundamental problem that SVMs were built to solve? Well, it all starts with something that sounds incredibly simple, just drawing a line.
So, let's start with a basic job. We've got these two groups of data points, the blue squares over here, the yellow circles over there. Our goal? Draw a line to separate them. Seems easy enough, right?
Well, here's the catch. I could draw a line here, or maybe tilt it a bit, like this, or I could squeeze it right up against the yellow circles. The fact is, for this data, there are basically an infinite number of lines that could do the job. So that leads us to the real question. If there are tons of lines that seem to work, how do we pick the best one? Which line is the most robust, the one that's most likely to do a good job classifying new data that it's never seen before?
And this is where the first stroke of genius behind SVMs comes in. It's a beautiful, elegant answer called large margin classification.
Instead of thinking about drawing a thin line, I want you to imagine paving a street. An SVM's goal isn't just to separate the classes, it's to find the absolute widest possible street that it can fit between them. The bigger the gap, the better. We call this gap the margin, and our decision boundary is the line running right down the middle of that street. And this brings us to the most important players in this whole game, the data points that are sitting right on the curb, the ones that are literally defining how wide our street can be. Those are called support vectors. They're literally supporting the whole structure. And here's the really mind-blowing part. Only those support vectors matter. That's it. You could add 1,000 more blue squares way off in the distance, and our street wouldn't change one bit. The entire model is defined only by those few critical points on the edge. That's what makes SVMs so incredibly memory efficient.
Now, this maximum margin idea is fantastic for perfectly separated data. But let's be real. Real-world data is almost never that clean. It's messy. So, what happens when you get an outlier? You know, a single blue square that's on the wrong side of the neighborhood. All of a sudden, our super strict rule that there can be nothing on our street becomes impossible. This rigid approach is called a hard margin, and it just breaks down here.
The solution is to get a little more flexible. This is what we call soft margin classification. Now the model has a new goal. It still wants to find the widest street it can, but it's willing to strike a deal. It'll tolerate a few points being on the street or even completely on the wrong side. We call those little errors margin violations.
And we control this trade-off with a really important tuning knob called the C hyperparameter. Think of C as a strictness style. A low value for C tells the model to prioritize a wide street even if it means tolerating more mistakes. That can sometimes underfit. But if you crank C way up, you're telling it to be super stripped, creating a narrower street to avoid as many violations as possible, which runs the risk of overfitting. Finding that just right value for C is the name of the game.
Okay, so a soft margin lets us handle data that's mostly linear. But what happens when the data isn't linear at all? What do you do when a straight line, no matter how you draw it, just won't work?
Take a look at this. This is the classic Moons dataset. There is absolutely no way you can draw a single straight line to cleanly separate the blue squares from the green triangles. It's just impossible. A linear classifier is totally useless here.
The solution here is one of the most beautiful and, frankly, mind-bending ideas in machine learning. Instead of trying to draw a complicated curvy line, the SVM does something incredible. It projects the data into a higher dimension. And in that new dimension, the data magically becomes linearly separable. You can just slice it cleanly with a simple, flat plane.
Let me make this more concrete. Imagine your data is just on a number line, in 1D, and you can't separate the groups with a single cut. But what if we add a second dimension? Let's say we just square the value of each point's position. All of a sudden, our 1D mess becomes a nice, clean 2D parabola.
And now, look, we can just draw a simple horizontal line to separate the data perfectly. That's the core idea.
Now you're probably thinking, okay, but creating new dimensions and transforming all my data, that sounds really, really slow and expensive. And you'd be right. But this is where the real magic comes in. It's called the kernel trick. It is, for all intents and purposes, a mathematical cheat code. It's a function that figures out how the points relate to each other as if they were in that higher dimension, without ever actually doing the expensive work of transforming them. We get all the power without the pain. It's brilliant. So let's bring it all back to reality. When should you actually reach for this sharp knife in your data science toolkit? When you're actually using this in your code, you'll be tuning these key knobs. We've talked about C, which controls the margin flexibility. The other big one is gamma, which basically controls how far the influence of a single data point reaches. A small gamma means a smoother, wider-reaching boundary. A large gamma means the influence is very local, which can lead to more complex, wiggly boundaries. The real art is in finding that perfect blend of C and gamma to create the best possible model.
So here's the bottom line. The pros: SVMs are amazing in high-dimensional spaces. They are incredibly memory efficient since they only care about those support vectors, and they're great when there's a clear separation. The cons: they can get really slow on huge data sets. They can struggle with very noisy data where the classes overlap a lot, and they don't naturally give you probability scores.
And that leaves us with one final thought to chew on. The kernel trick. It's more than just a piece of math. It's a powerful lesson in problem solving. It teaches us that a problem that looks completely impossible from one angle might become dead simple if you just find the right way to look at it. It really makes you wonder, doesn't it? What other impossible problems could we solve just by finding a new perspective?